now for something completely different. Am I up, running? Hey, can somebody give me some kind of idea of how much time I have? Like, how much?
Oh, you have 30 minutes.
Okay, so I have too many slides for that, so I'm going to edit these on the fly. And, well, as it happens. So I'm really pleased that my colleagues did such a fantastic job of covering the product space. I never do that, as you guys know. That's not my thing. And you'll see in my slides, I'm kind of a network geek. I'm a network geek, but I'm also a guitar geek, and I'm also a math geek. So I'll try to hold all of that stuff down. So what I did was, I've been working around SDN since it was new, and I've been looking at it, and I've been looking at all the things going on, and I started thinking, what is really going on here, And this is kind of the synthesis of those thoughts. So, and stop me anytime because this is going to be quite a bit different than what you've heard. So here's what I'm thinking. What was the hypothesis behind all of this stuff, and what is the problem space? Then there's a bunch of trends going on. What are they, and how are they inducing this kind of new landscape that we're seeing? A little bit about the past. This is where I'll talk a little bit about OpenFlow in here, and then we'll just keep going. So, yeah, this is intended to be controversial and maybe a bit sciencey. So stop me if you don't like it, but watch out.
Bring it.
Yeah. Okay. So this is the whole thing that really occurred to me, or that I realized in looking at this, is that we're talking about all this stuff, but the reality is the software-defined network world is going to bring us all kinds of uncertainty, randomness, and volatility to networks that we've never seen before. And I'll explain why and how in a second. But basically, what I want to know, and I think everybody wants to know, is why is this, if it's true? How is SDN and really the rise of software, everything in general, accelerating this effect? And finally, what might we do to take advantage of it? Now, my friend Sean Duran, I don't know if folks know Sean Duran, but I asked him to review these slides, and he kind of edited this and said, maybe instead of taking advantage of it, you might want to say survive it. But I still think there might be a way to take advantage of it. So, lots of words here, but basically, the hypothesis, the problem that people were trying to solve is, okay, I'm a network, I'm an enterprise operator, I'm a data center operator, I'm a SP. My job is to provide, this basically state-of-the-art network infrastructure and services while just minimizing the cost of the whole thing. And that's what everybody's trying to do. And so it was back in the days of Stanford that people were saying, well, it's really caused, the real problem here is there's an inability to innovate in the underlying network, and there's no abstractions. And so, you can look at this and you go, okay, well, the requirements of the network are all stated informally, out of band, statically. We don't have programmatic interfaces, and we know it would be better if we had programmatic automation of configuration management, et cetera. And even in the early days, people were saying, hey, we've got to write new control planes, and more than that. Actually, the early days of all of this, and part of the structure of OpenFlow is kind of legacy from this, is that people wanted to write new network layers, different IP layers. And so for the most part, all that's true. But the question is, do we need to radically change the network architecture to accomplish this? And so hold on to that, because I'm wondering about that myself. And then I'll just note this, is that how people always say, oh no, don't skate to where the puck is, skate to where it's going to be. My argument is that because that curve is unknowable, and this is really a consequence of the software world that we're entering right now, coupled with Moore's law, unbelievable amount of compute available to do this with. And then now that we have software-defined networking, it's all open loop control, right? Because there's humans typing software, right? And given all of that, there's a bunch of research from different fields that really suggests that this is all this kind of uncertainty is inevitable. It has to happen. So what was the problem these guys were trying to solve with all of this? Well, maybe it's this, right? I mean, maybe it's that you get these complicated networks that have these three problems. First off, there's no general purpose way of talking about a forwarding plane, right? So the router has a forwarding plane, the firewall. We talked about that today. The whole thing's myopic, right? We look at boxes. The whole management thing was about boxes. And then the final thing is that basically configuration and policy is all intertwined, right? When you write your policy, it's an ACL, right, or something like that. That seemed to be a problem. It's all intertwined. And the network was like the database of record. terrible stuff, hard to maintain. Or maybe this, we're responsible for this, the IETF guys are responsible for this. We like to build protocols, so you wind up having a mobile phone that looks like that, and that has some consequences, like it's fragile, and really what's the problem though? And, and then I was thinking about this, and I'm thinking, well, what is even fragility and what's robustness? So I went off and I met some guys who were in the quantitative risk management or in engineering field, and they had a really nice definition of what fragility was. And I think some of you guys know I've been working on in the systems complexity field for years and years.
A paper from 10, 15 years ago about network fragility.
Yeah.
Fascinating read.
Well, this stuff is even more interesting, and I'll explain some of it. So basically, when you have a system like the internet, you get this. I drew this picture a long time ago, and I can't find the source, so I can't modify it. But the thing is that when you have robustness and complexity, it's really with respect to some property, and that's what's wrong with this picture. But give me that for a second. So what happens is, as you get more policies, more protocols, more configurations, more interactions, what you're really doing is you're trying to build robustness into your network. That's why you do it, right? And so, but the curve, the robustness versus complexity curve always winds up looking like this. In other words, it's a heavy tail thing, right? And what it means is there's some value at which, if you go past, things are getting better, now it's all pain, right? And it gets painful fast. And we've seen this in networks a lot. And so, over here is where you're robust, and over there is where you lose your job. Or you wish you would.
Yeah, usually wish.
So this is sort of the complexity theory, systems theory, control theory curve. Everybody's seen this a million times. So what is robustness? Well, let's just make it simple. One of these systems, like one of these big network systems, is robust if some property of the system doesn't change when something happens to it, right? It's robust, right? So the routing system, it's robust. If a router goes down, we route around it. It's robust. Fragility is the opposite of that. But I'll just note right here, it's really a second-order effect, and it has to do with acceleration, and I'll talk about that in a second, but that's related to the software world. And there's another interesting thing here is that a system can have this property where it's robust to something, but it's fragile to something else. And in fact, for these certain kinds of systems, which are called RYF or robust yet fragile systems, it turns out that if you create robustness, you will create fragility. Let me give an example. I got a building, I have one router interface into it. I want to be more robust than that because I don't want all the hosts to carry routing, right? I want to have HSRP and give them a default, right? So I built HSRP. Okay, now I'm robust to the failure of one router, but I'm not robust to the failure of the HSRP protocol screwing up the MAC addresses, right? And that happened all the time, right? So, before VRP and all that stuff. So basically what you did was you created robustness in one place, but you exposed another fragility. And then what you do is you create another kind of, complexity on top of that, and you get in this spiral. So, you can think of this as like, you can have a system with high efficiency, which kind of means it uses minimal resources, but it's unreliable because of that, because you optimized it, right? So there's a paper for it. You guys can have these slides too, by the way.
It's a great white paper, by the way.
What's that?
I've read that white paper.
Oh, yeah. Yeah, John Doyle's a fantastic dude. If you ever get a chance to meet him, definitely.
Yeah, no, it's a great white paper. It really explains this RYF.
Yeah. So, if you step back and you go, what is all this about? You go, well, okay, reliability is kind of robustness to component failures. That's what reliability is. Efficiency is robustness to resource scarcity. Scalability is, robustness to changes in size and complexity. Modularity is, component rearrangements. And evolvability means, you can kind of roll with changes over long time scales. And we want all of those things, by the way, in our network. All right, so scaling. All right, I'll just geek out for a second here. What's really interesting about all of this, this is actually I learned from the quant guys. What's really interesting about all of this is that for these fragile systems like the internet is fragile, it turns out that they have to be non-linearly fragile. So in other words, let me give it for an example. If I take a coffee cup or now this will be easier. If I jump off a block that's 1 foot high 30 times, I'll probably be okay. I might get shin splints or something, but I'll be okay. If I jump off a 30-foot thing one time, I will not be okay. right? So there's nonlinear, and it's nonlinear, right? I mean, if it were linear, the damage from walking around would have killed me a long time ago. So nature's actually requiring this property of us, not only physical things, but of our network too. And so, this is a little bit of math that says it, right? Basically, it says if there's a sort of a harm function, the harm by the one big thing has to be less because the harm function's negative than n times the smaller one. That's kind of what it's saying, right? And it's, oddly enough, it's related to what we call scaling. The network guys go, oh, it scales like n squared. How many times have you said that? I've said that 1,000,000 times, at least. What does that really mean? It really means that the damage to the network has constant acceleration. In other words, it's a second order effect. The second derivative of this is 2 for really weird sized things, like when things get really big. And that's what it really means. So they're the same thing. They're kind of like the flip side of the same thing. And it really means you suffer this kind of nonlinear harm from big events, tail events that don't happen much. You hope they don't happen much. So here's a picture of it. Let's skip that. But basically, when things are small, it's all good. And then when things start getting far away from normal, things get really bad, fast. And we've seen that a lot. AS7007. Routing works really good until it doesn't. Okay, anti-fragility is a really crazily cool idea. I don't know if you've heard about this. It's an idea from a guy named Talab. Basically, we have these systems that actually get better when they're perturbed. And they're all the dynamic systems. But as engineers, we try, so they thrive on randomness, on volatility, and all of that sort of thing. There's a lot of examples of this I can give you if we have time. But you might want to know, could I actually build a network that had that property? I'm not sure. It'd be learning. It'd have some learning component. So complexity, okay, this is a really nice thing. Here's another nice paper if you want to read it. But basically what it comes down to, complexity is not what we used to think of it as. It's really structure that's in place to deal with uncertainty. And nature does it. We do it in our networks. We do it in everything we build. So basically it's this. Design strategies intended to create robustness to uncertainty. That's what it is. Structure. Okay, so now back to this macro trend thing. Oh, by the way, when I can't find a picture from my slide, I usually take the title of the slide and I type it into Google Images, see what I get. I got that. I like that picture. I don't know what it has to do with this. I just like the picture. Okay, so there's these macro trends. Remember I said I was looking at this stuff and I'm going, what is really going on here? So I have a biology background. I like math. I like science. I like that kind of stuff. I'm looking at this and I'm going, okay, well, this evolution of intelligence that we're seeing in the network is really the same as what you see in nature. It's not really that different. And oh, by the way, when I was at Cisco, I showed this thing and people melted down and said, oh, what do you mean? We build hardware. But what I wanted to point out was, the hardware thing is still there. At some point, somebody's, having this still be there means somebody's going to have to forward packets on the wire at some time, right? Eventually, unless it's a V switch or whatever, but eventually. And so there's all these things when you start looking at this that are architectural themes that you see in our network and that software is critical to. And like, for example, this is not a complete list, but a few of them. Thin waisted architecture, so I'll talk about that in a second. Massively distributed systems, BGP, the amine system. Highly layered, robust control loops, TCP, IP, amine system, and component reuse. Do people know how traceroute works? There's no traceroute protocol. Well, for MPLS there is, but there's no traceroute protocol. It reused ICMP, TTL exceeded. So here's my conclusion. There's one other kind of nice thing about this is that there's this punctuated equilibrium model of evolution, but it requires exactly this property to work. So it's pretty interesting. So all this stuff started to come together in my mind.
So you're positing that punctuated equilibrium applies to the advancement of networking? Is that what you're suggesting?
Yeah.
Okay.
It's all the same thing, actually. So remember I said, thin waist, right? So there's this really interesting idea from biological systems theory called constraints that deconstrain, and they call this thing a bow tie for kind of obvious reasons. And this was the knot, right? And the idea here is that there are constraints that deconstrain because this thing is constrained. And then everybody out here can do whatever they want. They can build it on top of this thing. It's stable, right? And likewise, it can take inputs of all sorts and create sort of, this is almost like formatting the data, right? And you know, nature has this all over the place. ATP metabolism is the best example of this. But wait a second. I think I've seen this before. Yeah. So you step back and you go, well, there's really something going on here, right? I mean, this is an architectural primitive that if you're going to build a system that's evolvable and scales, it's going to look like this, right? So it's going to be bow tie architecture or have these constraints that deconstrain. And, you know, I sent it, you know, when I realized this, I sent an email to Vince Cerf and I said, how'd you guys come up with this? You know, and he gave me a long explanation of it, but what it came down to is they knew that there were going to be a bunch of stuff down here, and they were hoping there would be a bunch of stuff up here. And so they just hit it, right? I mean,
It seems obvious.
yeah.
It isn't obvious, but it seems.
Retrospectives make a lot of things obvious, you know.
Yeah.
But anyway, so this is interesting. Now, I hope I have this slide here. But now that you kind of look at this and go, okay, that's interesting. Oh, here's another thing. There's an apparent paradox, right? I mean, the components of in biology, all these things on the right, the components are all really uncertain. They all break and they don't work all the time. But somehow the system becomes robust, right? Well, what about TCP/IP systems? It's the same, right? It's the same. We built it originally for the components not to be robust. You know, nuclear war and all that. So it's another thing where it's the same thing. Okay, so then I started thinking, okay, what is OpenFlow SDN? I'm calling it OpenFlow SDN because later on I'll tell you that OpenFlow SDN isn't the only kind of SDN. And some of my colleagues alluded to that. So is it here? It's certainly not here. So if this is right and you miss the hourglass, what is it saying architecturally? I don't know the answer to that. I'm asking. Okay, I'll get back to that.
Yeah.
So here's another macro trend. Everything is de-siloing, right? So vendors want to sell end-to-end solutions, not the way of the future. It's going from vertical to horizontal integration, open everything, right? Open APIs, open protocols, open source, right? Everything pluggable. So this is my conclusion. For networking, it's this. The future's about ecosystems.
Yeah, absolutely.
There's another one, network-centric to IT-centric. I think we heard about network function virtualization and all that stuff. There's a million of these things out there where people are trying to get the advantages of scale that IT had and bring them to computing, to networking. And so the summary is this. People know what DevOps is, right? Yeah. This is a summary. Other things, everything virtualizes, yes. Data center is the new center of the universe, yes. Integrated orchestration of everything, yes. So the bottom line is increasing influence of software everywhere. And it's all integrated, right? It's all integrated with compute, storage, networking, identity, all of that stuff. So the increasing power of all of this stuff means that uncertainty and volatility is increasing as well. Because humans are making software. And that's where it all goes wrong, in general. No. Okay, so how did we get here? Now we're here, and we're going, oh, well, we have OpenFlow and SDN, and we're going to have software everything, and that's all very, very nice. How did we get here? So the idea was everything was too vertically integrated. And it goes without saying that that really made the job of the network researcher difficult. In fact, the people at Stanford who wanted to experiment with new kinds of control planes used to think they had to do it on embedded systems like routers. And so they wanted to have open systems. And I remember a lot of times, like when the Genie project started when I was at Cisco, they wanted to have source code to the CRS because that's the way they thought about doing it, because it was vertically integrated. So I just asked another question. Is there really a relationship between that and fielding a production network? There is, but what is it? So what's the history of this? It's pretty interesting. It's the same gang of 3 or 4 and all of this stuff. So Martin Casado had a project called SANE, which was really a security architecture, right? And you can imagine how this was going to work. I had a controller somewhere, and it was going to program ACLs on the edge of the network, right? And that was called SANE. And then they had Ethernet SANE. This is Martin's picture, and this is a typo. And then they had Ethernet SANE, which was SANE for Ethernet, and then they had NOx. And they actually had something called InSANE, which was Internet SANE. But the salient things here is that you had centralized control, open interfaces to the data plane, and separation of control and data. That was what it was about, right? Those are the architectural features. Oh, I just put this in here, so if you want to find it, you can get on Martin's page on Stanford, which is still there. So we had SANE. Then a little bit later, this whole thing at Gates 104, I don't know if you've heard about this, but these guys gathered on the Stanford campus in the Gates building, computer science, on Tuesday afternoons and came up with this. And this is what we know and love as OpenFlow. So I'm not going to do this because you guys know all about this, but I will ask one question. If you look at the literature around this, one of the things that people were saying is, okay, we want to have the same thing happen in compute or in networking that happened in compute with respect to breaking down of vertical integration. Is this really the same thing as happened in compute? Think about it.
No, it's not.
Yeah, so I got this picture from James Hamilton, who's a cloud architect at Amazon, and he drew this picture. And as you can see here, what happened when it broke down is the architecture remained the same. It's just that interfaces opened, right? So when you have your Ubuntu box on your Intel platform, it's not architecturally different than if you have Windows on your Intel box, right? Or if you had VMS on your VAX. Architecturally not different, right? So we had this thing. This is such a famous picture, I don't know if I need to talk about it, but basically what I want to point out is the OpenFlow Controller thing and this northbound API. So as soon as you have this OpenFlow controller, and you want to, or any kind of controller really, any kind of centralized control infrastructure, and you want to have resilience and scale, it has to be distributed. So this was a fun toy, and actually Martin's thesis wasn't about this. So of course he built a centralized thing because it's way easier than building a distributed system, and he wasn't trying to demonstrate that, right? But what happens if you want to make this into a distributed system? Well, I hope I have a picture. Yeah. So basically now what people are saying is these things have to be logically centralized, which means distributed, by the way. I don't know why they say it distributed. But now once you have a distributed thing, it's logically centralized, it's a distributed system, and then you have to make a trade-off. A lot of hard trade-offs, like between whether or not the control plane can converge rapidly and the state consistency model. Like in the internet, we have something called eventual consistency, which means we don't know how long it's going to take or what's going to happen, but eventually it's going to get there. If you start giving a stricter constraint than that, like if you look at a database like Cassandra, they give you a menu of things like quorum, n over 2, all these different things. It has a huge effect on the rate at which this control plane can converge. And then you have to think about what are the implications of the loss of fate sharing between the control and data plane. So right now, if I got a router that has at least tightly coupled software, then when the interface goes down, I don't have a protocol on the wire to tell me that. There's a lot of things like that. So we take huge advantage of this fate sharing, and this breaks that apart. What are the implications of that? Oh yeah, and this is not new, right? I mean, here's a bunch of, nothing new under the sun. It's, but I will say that, some of these things have succeeded and some have not, for different reasons. SS7 did, closed system. So, okay, so here was OpenFlow Switch 1. The problem with this thing, too simple. There wasn't, and somebody mentioned it, there weren't feature functionality. It was L2 only and not all of L2, right? And there were expressiveness problems. Like you couldn't express certain things that you wanted to say, right? And so time went by, and then we got this, right? This is OpenFlow 1X, right? This also, and the idea here, by the way, the idea here is kind of interesting. So a packet comes in, and instead of, you can actually execute the actions associated with the match, but you don't have to. You can collect them all in this action set thing, and then wait until you have no more go-tos, basically, and then you can execute them. And the reason for that was these tables were going to have orthogonal functionality, so they all wanted to see the original packet. So you couldn't actually modify the packet in flight through here. This thing's now a network, by the way. You couldn't modify the packet because the result down here is unpredictable. You don't know. So how can you put a match in there? So the questions that you have to ask about this are, why this design? Well, the first problem was that if you have one table, you know how if you unroll a loop in a compiler, it just blows up because there's this cross product that happens. Well, there was a cross product that happened in this single table thing that was sort of like rules times policies. And so this was one way to get around it. But the problem now is, what's the complexity of this? Well, it's at least n factorial times something, right? N factorial because how many ways to choose this, n minus 1, whatever, right? And then at each table, you have L match bits. And so you could take 0 match bits, 1 match bit, and L match bits. So there's 2 to the L of those. And then for each one of those, there's actions. So this isn't even the whole number. I can't really figure out the exact number because it's not well enough to find. But so it's too complex. What is a flow? Can't really implement it on ASIC hardware, and that's what Kurt's group is trying to do. The table typing patterns are trying to make OpenFlow efficiently implementable on conventional ASIC hardware. Some people think, oh, well, the problem is that the ASIC vendors are making the wrong hardware. But we have what we have right now. There are all these really cool reasoning systems like Frenetic. Does anybody know what Frenetic was? It's something done by Jen Rexford and Nate Foster at Princeton and Nate Foster at Cornell. That requires a single table right now because you have to know what a flow is. You don't really know what a flow is here. There's no fixes for the lossy abstractions. I can talk about that. It goes both ways. So to get from the switch to the controller, you have to what we call leak information because the actual protocol doesn't carry what you need. So you have to know about the 5 minutes. Oh, wow. OK. Forget that. All right. Yeah, 5 minutes. I'm not. Yeah. All right. So let me. I kind of cooked up this SDN Continuum idea, right? And the idea is on sort of one polar side of this, you have something like what I used to call it OpenFlow SDN, but I just call it data plane SDN now. And that's where you have this complete separation of the control plane and the data plane, open interface to a programmable data plane, and this is like OpenFlow, forces, and this stuff. And initially, the applications were programming the network, right? I mean, people thought, oh, I'm going to have an application that actually programs the network, like a user application, right? That's since morphed, right? Kind of in the middle somewhere, you have what I'm calling control plane SDN. It retains the existing control planes, and they're made programmable. So you have things like I2RS, BGPLS, all of this stuff. And they're network-aware applications now. So now the network can know about the state, but it's really requiring that it modifies its own behavior, and the network will take care of a lot of the parts of this. So, and this is, like I said, PCE is an example of this, I2RS, and various vendor SDKs and things like that. And then you can go all the way to the other side, and you'll have this overlay SDN thing. Okay, this is Nicira VMware, right? So basically, it retains the existing simplified control and data planes, whatever is there. They're saying, give me 32, 64, 128 by 10 or 100 ECMP, and I'll lay a complete control plane on top of that, and I don't really care about what's underneath that. So there's a whole spectrum of things going on out there. So I typed that into Google Images, and that's what I got. I kind of
Why
like
not
that.
Zoidberg?
Yeah, and he's drowning in garbage, if you notice. No, my grandson Jack loves Zoidberg, so it all's perfect. No, but more seriously. So I had to cut out a lot of this because of time, but basically the high order bit here is, these systems we're building now, they're inherently uncertain, and it's going to get worse. And we're not prepared for this, right? This is the unseen consequence of all this stuff we're doing. We need to start architecting for rapid change and rapid evolution. We don't do that either, right? And extreme programming or agile methodology, software engineering methodologies kind of give a clue about how you might do that. I mentioned this software programmability, Moore's law. It just means everything's going to be less certain. And the lucky thing for many of us in the network business is that we work around I've worked in the service providers mostly, and they work around the narrow waist. But if you're a cloud provider, all bets are off. And I'll tell you, how about, anybody seen SpotCloud? You check this out? Okay, so this is a spot market for compute. And what they did was they built a cloud, OpenStack cloud, and they provide a connector for a buyer and for a seller. And if I'm a buyer, I can buy compute VMs anywhere on the planet because the seller can be anywhere. And now I can build a cloud that I lay over the top of, say, EC2, where the other endpoints are anywhere, right? So basically, the Amazon guys have no visibility into this. I mean, so this is causing, and by the way, spot markets are the most volatile markets there are, right? So you know that this is going to be, if this takes off, this is going to play havoc with anybody's traffic engineering, right? And by the way, it's real-time dynamic, too.
Amazon's already had problems with their spot market where the swings just go crazy because people are just shoveling VMs over there because it's the cheapest thing they can find, not realizing that if they don't pay attention to what's going on, it becomes the most expensive thing they've ever seen.
Yeah, and they don't have visibility either. They have no way of knowing this, right? I mean, in their own spot market, they can, but third parties, there's no way. You know, there are no hooks. There's nothing, right? So I also think that the conventional technology curve, speeds and feeds, all this Moore's law, you know, this is the reptilian thing I'm talking about, it's Moore's law. Someone has to forward packets. That stuff's going to all continue. 400 gig, terabit, all of that stuff is in the relatively near term. Silicon photonics, we're all been looking at that. Denser cores, I've seen 96 core, you know, general purpose CPUs, not even GPUs now. So that's all happening. And this is all going to contribute to the uncertainty in all this. So again, future all about ecosystems. Open source consortium. That's another thing that's going to inject uncertainty in here because, you know, when you're in the standards world, you're kind of, things are a little bit more rigid. Here you're going as fast as people commit decent code, right? It's a different thing. Oh, let me just show you what I think the platform might look like. So it's kind of I'm out of time? Yeah. I'm done. Okay, let me just show you this and then I'll go.
I'm ready to visit you.
What's that? Get the hook?
Yeah, I got the big
all right,
hook here.
All right. Can I say this 1 minute?
Yes.
So what I, no? Yes?
Yes. We love you. You can finish it. Yes.
I'll just say this one. So basically the deal here is what's emerging is these middleware layers, right? And they orchestrate between basically what are OSS, BSS kind of applications, user applications, and other kinds of applications that live at various layers in here. But basically the key thing is that southbound, it's going to be OpenFlow, but it's also going to be all these things too, right? You know, and there'll be this new bidirectional information flow. This is also going to increase the volatility of things. And then of course, you know, you'll have OpenFlow controllers, you'll have multi-layer PCE, all of that stuff, and middleware though. So now this is all software. So again, more of the same. Anyway, that's my view of it.
Can I ask a quick question? Do I have time? I know, sorry. So you brought up a key construct that when we went to server virtualization, it was the same platform. Network, we said we were going to do that, but we didn't. So if you look at what Cisco is doing, just based on the discussion we had yesterday with 1PK and stuff,
yeah,
they're
1PK.
effectively saying they're going to open up their existing architecture to something like virtualization. I mean, it's not going to be across the board because of a private vendor.
Yeah. 1PK is going to live down here, right? 1PK is an interface that you use to talk to the switching infrastructure or whatever you want to call it.
So I guess the overarching question is, are we just stuck with the fact that networking won't ever mirror the server virtualization side, or will we evolve to there in your mind? That we're going to evolve to just open class of hardware?
Yeah. No, but it might happen in a different way, like white boxes.
Okay.
So if I put a, say I built an open source network OS, you know, an open source version of iOS, or something like that.
Something like Viata maybe.
Yeah, something like Viata. And I put that on a white box. I think that would be more analogous to what happened in the compute world than what's going on with OpenFlow, because that's a new architecture.